Welcome, everybody, and thank you so much for joining us today. My name is Paul Donahue. I will be the host of today's session. And just a few protocols to start. We'll keep everyone on mute, which I think will optimize our audio. And you can pose questions at any time using the chat feature. For those of you that are not familiar with Zoom, if you hover your mouse, depending on your browser, at the top of the screen or at the bottom, you should see the option. And please direct your questions to me. We will save some time at the end to address questions. And if we don't get to them all, we'll be sure to send them out the answers out electronically. So I think this way, if you'd like to pose a question anonymously, it provides that comfort level. And also it minimizes the chance of us having some audio issues. So as I think you know, this is the first of what will be a series of webinars or tutorials. And the objective here is to share facts and maybe a few figures and relevant information about RF components, what they do, how they do it, different configurations, what's different about one versus another, related technology. And certainly we'd like to talk a bit each time about the significant sometimes enhancements from a design perspective and from an engineering perspective, the things that have to be added or the innovations that have to be added to these components to make them fit into customer devices. So that said, you probably know that TRM Microwave makes a variety of these components, hybrids, combiners, and of course, the power dividers, which is the topic of today's session. And these are relatively small components that fit inside larger devices, possibly inside a radio or a two-way receiver. And a power divider's primary functions are to split incoming power and direct it to the right places inside these devices, and to also absorb any excess power so that that power doesn't wind up in the wrong places within the devices. And for example, a radio might have more than one antenna. So the power divider would split incoming power, direct it to each of the antennas, and it would make sure that any excess or unused power is absorbed so that it doesn't interfere, say, with the radio's reception or damage other components internally. To execute their mission, these power dividers, as you can imagine, have to operate reliably and repeatedly over time. And as we alluded to earlier, they've got to conform to a wide range of specifications, customized specifications, so that they fit inside the customer assemblies. So this is what we want to talk about today. And I'm very happy to introduce our Chief Technology Officer, Shaun Moore, who's going to lead the session. As you probably know, or you may know, Shaun joined us back in the 90s. He came to us with a fair amount of industry experience and a real passion for solving problems. And his skills in those areas have done nothing but grow ever since. So Shaun, let me turn this over to you, and maybe you'd like to start by giving us a little summary of your objectives for today.
Sure, thank you, Paul. So basically for today, what I'd like to accomplish really is to go over some very high level theory as far as to what a power divider does. Why would you want to use a power divider? And then from there, launch into what a power divider, how do you actually build a power divider as far as to different topologies. There are many different things within different technologies that allow different sorts of advantages to one construction over the other. I'm going to discuss some of that. Then I want to go into really what makes TRM power dividers different than anybody else's. What are our differentiators? And then I'm going to touch a little bit on combiners. Combiners very often get thought of as being a reciprocal of a power divider, and at one level they are. However, in applications, they usually turn into something that's a very different sort of a need, and therefore the designs need to be different. That actually, the combining will actually be one of our next webinars that we're going to be talking about in detail for that as we get into those sorts of details. And then, of course, we'll wrap it up.
Terrific. And Maybe next it would be a good idea if you could give us a more professional definition of power dividers. I'm not so sure that my layman's version really covered it effectively.
Sure. At a basic level, power dividers take a common signal, and this could be from a single radio, a local oscillator, or any other signal source that's available on the platform, and it will distribute it equally to a variety of sources. Applications for this can include feed networks for antennas, antenna arrays network, like I mentioned earlier, local oscillator signal distribution, or just simply rerouting signals between modules. Very often, a single output of a module, we need to go to 2 or 3 places within the system, and power dividers accomplish this. And so it takes an RF signal and distributes it equally or unequally. Very often we do power dividers that have unequal tapers as well. In that case, usually for antenna array feed networks, where you want to have a little bit of a taper on the array to help control your side lobes, we do that as well. But at a high level, they're really used to distribute signals throughout the system.
Okay. Now, you mentioned combiners a few minutes ago, and I've noticed people often do talk about dividers and combiners at the same time. Maybe you could also define power combiners.
Sure. Power combiners, like I said, like I alluded to earlier, are really nothing other than networks that combine signals. Now, the tricky part here is that when you combine a signal, the combining actually happens vectorially. So each signal is a vector. There is an amplitude and a phase associated with it, and these vectors add with each other. The thing to keep in mind is that, and for an application standpoint, really what we're looking for is you can use power combiners either for taking multiple radios off of a single antenna, or if we're driving the antenna itself, we can take multiple amplifiers and combine them together to generate higher power for that. Like I said, they are reciprocals of each other, but then again, I'm going to get to a little bit later on as far as to what really the big difference is and why we have to build different devices for combiners rather than power dividers.
Okay, well, that makes sense. I've also heard people refer to power dividers as being passive. What exactly does that mean, Shaun?
Yeah, sure. So now for passive components means that we don't have to plug it in, for a power source. What that means at a bigger level is that the signal that drives the unit also powers the unit, which means there is no additional power source to there. As a result of that, a passive component cannot create energy. Therefore, the entire energy that gets input to the unit needs to get divided up and then output to the device. So if we have a two-way power divider, for example, and there's one input and there's 2 outputs, each output will have half the power of what is put into it. Or if we talk about it in dB levels, half power is minus 3 dB. A 4-way power divider, for example, will be one quarter of the power, or minus 6 dB down at each of the appropriate outputs. So the power and the energy that goes into it gets just redistributed. The energy cannot be created or destroyed, therefore it is just redistributed.
I see split loss there on the screen. I'm somewhat familiar with insertion loss. What's the difference between split loss and insertion loss?
Sure. So insertion loss is specified as non-recoverable energy. I had just mentioned that we have division, whether we go from one input to two outputs. That means we have 3 dB worth of split loss. In addition to that, there is some loss in the materials. The metal has some loss, the dielectric has some loss. So that is defined as non-recoverable energy. When we specify power dividers, the insertion loss is defined as a non-recoverable energy. And again, that usually comes up as being a number of a half a dB or 3/4 of a dB or something along those lines. So for a two-way power divider, what happens is you have the split loss and then you have the insertion loss on top of that. So if you have a half a dB worth of insertion loss, that means that if you add that on top of your 3 dB worth of split loss, your total insertion of each one of those through paths will be 3.5 dB. It's important to understand that that as we're coming through these sorts of dividers, that there is a difference between split loss and the way that we just and the way that that theoretically just happens, as well as the non-recoverable energy. That's important to really to consider when you're doing system analysis. And I think most system engineers are cognizant of this, although we have to be careful when we define this. But since we cannot create energy for a two-way power divider, and we say that there is 0.5 dB worth of insertion loss, we have to realize that we're not going to get minus 0.5 dB on two outputs. What we're really going to get is minus 3.5 dB on two outputs.
Okay. How does all this compare, say, to managing the power that just comes into our offices or into our homes?
Sure. At a very simple level, you like to think that if you take three wires, put them together, the power is going to divide itself. And at some level, it will do that. And that's what happens really in your house wiring. And at a DC level, what happens, and really from a power divider level standpoint for microwave circuits, we want to make sure that all sources and receivers have the same impedance. That ensures maximum power transfer from the source to the receiver. The universal sort of impedance that microwaves work with is 50 ohms. So what would happen if we were to take three 50 ohm ports, have one input and two outputs? The two outputs, the impedances would divide per Ohm's law, and we'd end up with 25 ohms that the source input would see. That would equate to about a 2-to-1 VSWR. So what would happen was with a 2-to-1 VSWR is that roughly 10% of the energy would not be received by the load and would be reflected back to the source. This is quite inefficient, and it causes other problems within the system. So what's important with any sort of power divider or splitter is that we maintain 50 ohms on all ports of the device.
Okay, and I might be the only one here today that doesn't know the answer to this, but what exactly is VSWR and why does that matter?
Yeah, so VSWR really is it is a measure of efficiency of how well the energy is transferred. VSWR stands for voltage standing wave ratio, and to visualize VSWR, a wave crossing the ocean is a good analogy. If you have a good VSWR, something a 1 point something to 1, that means that most of the energy is being transferred. Think about a wave going across the ocean. In that case, the wave is going across the ocean. Nothing's interfering with it. Energy is being transferred from one point to the next, and the energy is being transferred with being very efficient. What happens in a wave pool is that there is something blocking the wave. In that case, the energy hits the end of the wave pool, and then it bounces off the wall and bounces back to the source. That is what a high VSWR does. So energy no longer is transmitted across the ocean. It now gets blocked and gets bounced back. So in order to do that, there are various methods that we can do to make sure we have 50 ohms at all ports. And that's really what the essence of a power divider is. It's not just taking a bunch of parts and putting them into a common node and having the power go willy-nilly wherever it wants. We want to control where the energy goes and make sure we maintain 50 ohms at all the ports.
Okay, now, are there ways to match up the VSWR and the power divider, or do we always have to keep a high VSWR?
No, there are certainly ways to do that, and really the method that we do that really depends on the type of technology that we're working with, and each type of technology has limits as far as to what it can do. Some frequency limits, some bandwidth limits, and that's really I think that the next thing really that we're going to be looking at here.
All right, I also thought maybe you could give us some examples of different types of power dividers.
Sure. So at the simplest level, if we're working strictly with Ohm's law, it's very easy to go in there and put a few resistors in there. We can then take that 25 ohm node input impedance, and we can rebalance the network so that all of these ports will have 50 ohms looking into the network. This sort of a divider is called a resistive divider. TRM makes these. They are extremely broadbanded. TRM makes a DR285 that works from DC to 18 gigahertz, for example. Very broadband sorts of solutions. The downside of this is that it has twice the insertion loss of a non-resistive configuration. This is actually a big negative so for example, a two-way power divider, instead of having 3 dB worth of insertion loss, will have 6 dB worth of insertion loss. And also there is no isolation between the outputs. Since this is a symmetrical resistive network, any one input can be any one output, and therefore there's 6 dB worth of insertion loss between the outputs as well. So limited applications as far as that can tolerate that much additional insertion loss. Also parts where we really don't care about isolation, that's where this air could be used. It is extremely broadband, like I mentioned before. This will work right down to DC, right on through very high microwave frequencies.
Okay, so if a resistive divider is ideal for simpler level applications, how about another example for something that isn't quite so simple?
Sure. So what we get into next here is some transformer-based power dividers, or lumped element power dividers. These are exemplified by the DL series that TRM produces. These work quite well. Again, very broad frequency range, about 100-to-1 ratio. And these typically also work from frequencies of HF, right down to a couple of megahertz or kilohertz even, up through L-band, really have an effective height of somewhere right around 2 gigahertz. Popular bands for this are like 5 to 500 megahertz, or 20 megahertz to 2 gigahertz. These parts perform very well. They have good isolation, low insertion loss. Also, for these very low frequency parts, since the wavelength is so long, these produce very compact solutions for those sorts of frequency ranges. They're, like I said, they're a very popular part, and really they can be optimized to work quite well over broadband frequencies. Again, they're compact for the low frequency that they're designed to work over. The sort of negative for this sort of design is that they have a hard upper limit due to the parasitics of the transformer windings and capacitors and other junction capacitances that happen within these transformers. And really, once you get beyond that sort of barrier, the parasitics begin to really severely degrade performance at that point, and really this technology is no longer viable above about 2 gigahertz.
Okay, I think I get that. I've also heard people refer to a Wilkinson power divider. What's different about that type?
So a Wilkinson power divider is a distributed resonant length line. What happens here is that we use a line transformer to achieve the impedance bandwidth. The single section Wilkinson divider that's on your screen right now has roughly a 20% bandwidth. And it's very effective at higher frequencies, because now we have a distributed transmission line. Wavelengths get shorter and shorter at higher frequencies, this now becomes a viable size to build. What I will say is that by putting multiple sections in the power divider, as opposed to the single section shown here, you can easily get 10-to-1 bandwidths on this sort of construction. And again, TRM builds a wide variety of parts. We have octave bandwidth parts that are built out of 2 sections, as well as 9-section power dividers that handle the 2 to 18 kind of gigahertz bandwidths. Again, this over here works really well when you can get up to the higher frequencies. Really, the lower limit here, based on physical size, is somewheres in UHF. A couple hundred megahertz is really where the size starts to become unwieldy large. And the high end, it's a matter of how small you can make these transmission lines be effective based on the substrate that you're working on. TRM builds Wilkinson power dividers using both microstrip and strip line technology. The difference being whether or not we have a ground plane on the top or just one on the bottom. The actual math for both these dividers, whether it's the strip line or microstrip, is very similar. But it's a very effective of a way of building a power divider at higher frequencies. And like I say, there's actually one of our more popular sort of lines. This is exemplified by the DMS series of power dividers here at TRM.
Excellent. And I'm wondering, Shaun, if now might be a good time to talk about maybe some of the differences between power dividers and power combiners.
Yeah, sure. So I started to allude to this a little bit earlier. What I will say is that power combiners vectorially sum the energy from all the inputs. What this really means is that if the vectors do not align heel to toe this way, the energy gets subtracted. If the vectors start running this way and they're running equal and opposite to each other, all the energy will be canceled. Now, based on the laws of physics, energy cannot be created or destroyed. It simply means that it needs to get redirected somewhere. Where does all that energy go if it doesn't come out the common input? It gets dissipated in the isolation circuits of the power combiner. So based on that, what happens is that we have to accommodate all that power that needs to get dissipated. So things that affect the overall combining efficiency are things like the frequency relationship of the energy and the phase relationship of the energy. If we're running two signals that are exactly coherent in phase, equal amplitude, all the energy that's put into the power combiner will be delivered to the output. And therefore very little energy will be dissipated inside the isolation circuit of the power combiner. However, if signals are out of phase, or if there are different frequencies, varying amounts of energy will need to get dissipated. A good example of that is if you have two dissimilar signals, say you're running two different CDMA radios where there's different frequencies and different phases. Effectively, half of the energy from each input will be dissipated in the isolation circuit of the power divider, of the power combiner.
Okay, and I'm not sure I understand this 100%. You mentioned isolation circuit there, but are there also isolation combiners, or is that all part of the same thing?
It's really all part of the same thing. The isolation in the combiner is and really what happens there is all that excess energy that doesn't combine vectorially needs to go somewhere, and that goes into the isolation network of the power combiner. And really, this is most typically into the isolation resistors of the power combiner. This really has a really good reason as to why we like to use hybrids as power combining devices, because this way here we can port the energy off into a nice 50 ohm termination, and therefore we can get good thermal management on that. Again, that's topic for another day. But there are other topologies also, not just hybrids, that allow us to use 50 ohm terminations to dissipate that differential energy from the system.
Okay, how about speaking to some of the unique design requirements associated with these components?
Sure. Power combiners need to be designed for the worst case power dissipation. It is not just a matter of designing the circuit so that the transmission line running through the circuit handles the power, which really is the case for a power divider, but really for a power combiner, it's twofold. We have to make sure that the main line can handle that power, but in addition to that, we have to make sure that the isolation network or power dissipating circuit that's in there can be able to absorb that energy. As a result, really power combiners tend to be narrower bandwidth than its comparable power divider, and that is really due to the way that the network is actually configured. In order to be able to get the power being dissipated in a termination, the nature of the circuit that drives that divider typically has less bandwidth. And like I said, there are some very broadband structures that we can build as a power divider. Those resistor networks tend to be in a what we call a differential mode. And if they're in a differential mode, then there is not a good thermal path to ground. Whereas if we're in a single-ended mode, in that case, we can get a much better thermal path to ground. So power combiners we like to design with a single-ended approach for the termination as opposed to a differential mode for the termination. And that really limits our bandwidth. But again, that's topic for another day.
Yeah, that sounds like a good idea. So finally, maybe now would be a good time for you to tell us a little bit about the various design and engineering innovations that your team at TRM typically adds to these components so that they're effective in the field.
Sure. So what we like to do here at TRM is we never use only one technology. Very often, there are different different advantages, whether it's better isolation, whether it's better return loss, whether it's size, whether it's packaging, and we're not stuck in any one technology. And some of our competitors do one technology, but they don't do this other technology. TRM uses all the available technologies to be able to do this, whether it is lumped element, microstrip, strip line, coplanar waveguide, suspended strip line. The only technology we do not use is waveguide. And waveguide certainly has its advantages. It is something from a business standpoint, we have opted not to bring that in-house at this point. But once we get into these other sorts of dividers, very often it's very common for us to mix and match technologies in order to get the best performance for our customers. In addition to that, I will say that the packaging of how we work with the customers to come up with the exact packaging that the customers require is, again, one of our strengths and one of our differentiators. We are very happy to do that for our customers. Another item that we're quite happy to work with our customers on is testing and screening. That is something that we're certainly very happy to do that. We offer a lot of custom screening validation for our products as we're going through these designs, and that's something that a lot of customers really value, the fact that we'll go ahead and we'll take that extra mile and we'll do that additional ESS screening, or we'll go in there and we'll actually test it for RF leakage, or whatever those sorts of parameters are. I said custom packaging, as well as combining technologies for optimum size and performance.
Okay, well, this is certainly a lot of good information, Shaun, and maybe since we've covered so many different things, you could give us just a little summary.
Sure. So, power dividers have a wide set of possible applications. They provide a good way of distributing a well-conditioned signal throughout a network. They maintain good impedance matching on all the ports. And they also provide isolation between the outputs. Therefore, one subassembly and and another subassembly will not talk to each other through the power divider. The isolation network provides that. Power dividers can be used as signal combiners if we are talking about a relatively low, or we understand the nature of the signals of what we're trying to combine. Again, if we're talking about a very high power signal coming in there, we have to be very cognizant of the fact that the power handling capability of the isolation network may be compromised. And I will say that if you go into and you take a look at what the power ratings of our power dividers are, they all can be used as power combiners. However, the power rating is significantly degraded. A good example of that, for example, is the DMS series of power dividers, where we rate most of those at 30 watts input on the common port. As a power combiner, they're probably good for maybe a half a watt. So, there's a significant difference as far as what the power handling is if we're using that as a power combiner.
Okay, well, certainly you've cleared up a lot of good things there, and we don't have as much time as we'd hoped, but one question that did come up here, when you talked about packaging, the question was, does the packaging that you put around a part limit the types of technology that you can put inside the part?
The biggest difference there, Paul, really has to do with the size of the package. For example, I can package ferrite in a surface mount component as well as I can do strip line inside of a surface mount component. So those sorts of technologies can be used either in a surface mount or in a connectorized sort of component. Where you start getting limited as far as going into a surface mount component is thermal management. There we have to be very careful about what we can manage there. In addition to bandwidths, when you get into certain packages can be limited due to physical size that's available to us.
Okay, I think we're going to probably have to wrap up because we're running a bit over here. But certainly, we welcome any questions that you might come up with after the fact. You can see our engineering hotline number here. If you are one of our customers, we look forward to hearing from you. If you are one of our reps, you can certainly work directly through your CAM. You can also post questions, as you know, through the rep portal. And, you know, Shaun, I think that at the end of the day, from listening to what you've just said, I know that TRM technically sells hardware or components, but it just strikes me that your greatest sense of accomplishment comes from sharing innovative ideas and maybe helping the customers to come up with, I guess, collaborative solutions that get the job done. And that to me is the biggest value add that a manufacturer or a supplier can have. So good for you. Thank you so much for everybody joining us today. And Shaun, thank you. Nice job.
Yeah,
Take care, everybody.